You reach for a glass of water. Your brain knows exactly what to do. Extend your arm, open your fingers, grasp the glass, lift it smoothly to your lips. For most people, this happens automatically, like a well-rehearsed dance between mind and muscle. But for roughly 5 to 6% of children, and many adults who've never been diagnosed, this simple sequence becomes a complex puzzle their brain struggles to solve. They know what they want to do. They understand the goal perfectly. But somewhere between intention and action, the plan becomes difficult to execute consistently. This isn't clumsiness, it's dyspraxia, and what's happening in the brain is far more intricate than most people realize. Hey there, neurospicy folks! I'm Dr. Monty, and I'm an ADHD psychologist with a special interest in all things neurodivergent neuroscience. If you enjoy my videos, please consider subscribing to my channel to help me grow and bring more scientific understanding and awareness to a larger audience. Thanks so much! When most people hear dyspraxia, or developmental coordination disorder, they picture a clumsy child who trips over their own feet or struggles to catch a ball. The popular understanding treats it as a simple coordination problem, like having butterfingers or being naturally uncoordinated. Parents often hear phrases like, "they'll grow out of it," or "they just need more practice." Even many healthcare professionals miss the diagnosis, attributing the struggles to laziness, lack of motivation, or insufficient instruction. This surface-level understanding is compelling because it maps onto something we all recognize. We've all had moments of physical awkwardness, dropped things, or felt unsteady learning a new skill. It's easy to imagine that some people are just more prone to these moments. The medical establishment reinforced this view for decades. Researchers used terms like clumsy child syndrome from the 1960s through the early 1990s, as if poor coordination was the beginning and end of the story. But this picture misses something fundamental. Watch a child with dyspraxia attempt to tie their shoes, and you'll see something that doesn't fit the simple coordination model. They can describe the steps perfectly. They understand the goal. They may have tied shoes successfully yesterday, but today their fingers seem to forget the sequence. They start confidently, then pause, restart, get tangled in the laces, and eventually succeed through sheer determination and multiple attempts. It's not that they can't learn, it's that each time feels like the first time. The confusion deepens when you realize that dyspraxia affects individuals differently across various abilities. Some children with dyspraxia are highly verbal and intellectually capable. They might struggle to write by hand, but excel at storytelling. They might have trouble with sports, but show remarkable spatial reasoning in other contexts. This inconsistency baffles parents and teachers who expect motor difficulties to correlate with overall developmental delays. What we're actually looking at involves significant motor planning challenges alongside coordination difficulties. The motor planning component, how the brain organizes and sequences movements before they happen, is a crucial piece that reshapes our understanding of how the brain learns to move. To understand what goes wrong in dyspraxia, we need to understand what normally happens when your brain plans a movement. Think of motor planning like conducting an orchestra, but an orchestra where the musicians are scattered across a vast concert hall, the sheet music is written in multiple languages, and the conductor has to coordinate not just the performance, but also write the music in real time. When you decide to pick up that glass of water, your brain doesn't just send a simple grab command to your hand. Instead, it initiates an incredibly sophisticated planning process that happens largely below conscious awareness. First, your visual cortex analyzes the glass, its size, shape, distance, and weight based on visual cues. Your parietal cortex, particularly an area called the superior parietal lobule, integrates this visual information with your sense of where your body is in space, creating what neuroscientists call a motor affordance, essentially a prediction of how you can interact with the object. This information flows to your premotor cortex, which begins sketching out the movement sequence. But here's where it gets fascinating. Your brain doesn't plan the movement once, it generates multiple potential motor programs simultaneously, like a chess computer calculating several moves ahead. Your supplementary motor area weighs these options, selecting the most efficient path, while your cerebellum, that wrinkled structure at the back of your brain, runs rapid-fire simulations of the movement, predicting the sensory consequences of each potential action. Research using single-cell recordings in animal models has demonstrated this beautifully. Studies have shown that cerebellar neurons fire in precise patterns before movement begins, essentially pre-playing the sensory feedback the brain expects to receive. It's like your cerebellum is constantly running a virtual reality simulation of your movements, allowing your brain to correct errors before they happen. Once the plan is selected, your primary motor cortex sends the actual commands down the spinal cord to your muscles. But even then, the planning isn't finished. As you move, your cerebellum compares the actual sensory feedback, the weight of the glass, the resistance of your muscles, the visual feedback of your hand's position, with its predictions. When there's a mismatch, it sends rapid corrections back up to the motor cortex, fine-tuning the movement in real time. This entire process, from visual analysis to completed grasp, typically happens in a few hundred milliseconds. And critically, each successful repetition strengthens the neural pathways involved, making future performances more automatic and efficient. This is how you learn to tie your shoes, ride a bike, or type on a keyboard, through repeated cycles of planning, execution, feedback, and refinement. Now imagine this system with faulty wiring. In Dyspraxia, neuroimaging studies by Hayley Leonard at the University of Surrey and others have revealed disruptions at multiple points in this planning network. The cerebellum shows differences in activity patterns, particularly in regions involved in motor coordination and sequencing. The parietal cortex struggles to integrate sensory information effectively. Most critically, the connections between brain regions, the white matter pathways that carry information between the motor planning areas, show reduced integrity. Zwicker and colleagues at the University of British Columbia used diffusion tensor imaging in 2012 to map these connections in children with developmental coordination disorder. They found that the pathways connecting the cerebellum to the cerebral cortex and the connections within the parietal cortex itself showed significantly reduced organization compared to typically developing children. It's as if the orchestra is still there, but the communication lines between sections are fuzzy and unreliable. This explains why practice doesn't help the way it should in dyspraxia. Each movement attempt generates weak or inconsistent feedback, so the motor learning process that normally strengthens neural pathways operates inefficiently. The child with dyspraxia isn't failing to learn. Their brain is learning, but slowly and with much more effort than typical development requires. The planning difficulties extend beyond simple movements to complex sequences. Tasks like handwriting, which require precise timing and coordination of multiple muscle groups, become especially challenging. The brain must plan not just the shape of each letter, but the transitions between letters, the pressure of the pencil, the speed of movement, and the spatial organization of text on the page, all simultaneously. When the planning system is compromised, these multi-step sequences become overwhelming cognitive loads. The research picture becomes more complex when we examine what dyspraxia looks like across different populations and contexts. The condition affects roughly 5 to 6% of school-age children, according to large-scale studies, but diagnosis rates vary dramatically across countries and healthcare systems. In the UK, where awareness is higher, diagnosis rates approach the research prevalence. In the United States, many children with dyspraxia are either undiagnosed or misdiagnosed with other conditions. This diagnostic inconsistency reflects genuine uncertainty about where normal variation ends and clinical impairment begins. Motor skills exist on a continuum, and researchers continue to debate the precise criteria that distinguish dyspraxia from the lower end of typical development. The DSM-5 requires that motor difficulties significantly interfere with activities of daily living or academic achievement, but defining significantly remains subjective. Gender presents another puzzle. Early studies suggested dyspraxia affected boys more frequently than girls, with ratios ranging from 2:1 to 4:1. However, more recent research by Michelle Schoemaker at the University of Groningen suggests this may reflect diagnostic bias rather than true prevalence differences. Girls with dyspraxia may present differently, showing more subtle fine motor difficulties and internalizing their struggles rather than displaying the more obvious gross motor challenges that typically trigger referrals. The relationship between dyspraxia and other neurodevelopmental conditions adds further complexity. Roughly 50% of children diagnosed with ADHD also meet criteria for developmental coordination disorder, according to a 2019 meta-analysis by Kaiser and colleagues. Autism spectrum disorders frequently co-occur with motor planning difficulties. These overlaps suggest shared underlying neural mechanisms, but researchers haven't yet mapped the precise relationships between these conditions. Longitudinal studies reveal that dyspraxia's impact extends far beyond childhood motor difficulties. Amanda Kirby's research team at the University of South Wales has followed individuals with dyspraxia into adulthood, documenting persistent challenges with organization, time management, and executive function. The motor planning difficulties seem to reflect broader differences in how the brain organizes and sequences complex tasks, whether physical or cognitive. The intervention research presents mixed findings that highlight our incomplete understanding of the condition. Traditional occupational therapy approaches, focused on practicing specific motor skills, show limited transfer to untrained tasks. This makes sense given what we know about the underlying planning deficits. If the problem is in the planning system itself, practicing individual movements won't necessarily strengthen the broader network. More promising are approaches that target the planning process directly. Cognitive orientation to daily occupational performance, developed by Helene Politeco at the University of Toronto, teaches children explicit problem-solving strategies for motor tasks. Rather than drilling movements, children learn to verbally guide themselves through the planning process. What is my goal? What is my plan? How well did I do? Randomized controlled trials show this approach produces improvements that transfer to new tasks, suggesting it may address the core planning deficit. However, even these more targeted interventions show variable results. Some children respond dramatically, while others show minimal improvement despite intensive therapy. This heterogeneity suggests that dyspraxia may actually encompass several distinct subtypes with different underlying mechanisms, a possibility that current diagnostic criteria don't capture. Brain stimulation studies add another layer of complexity. Transcranial direct current stimulation applied to the cerebellum can temporarily improve motor learning in adults with coordination difficulties, but the effects are short-lived and don't consistently transfer to daily activities. This suggests that while we can influence the neural systems involved in dyspraxia, we don't yet understand how to create lasting changes in the planning networks. Understanding dyspraxia as involving significant motor planning challenges rather than simple coordination difficulty fundamentally changes how we should think about supporting individuals with this condition. If you're a parent watching your child struggle with seemingly basic tasks, the first crucial shift is recognizing that effort and determination aren't the issue. Your child isn't being careless or lazy. Their brain is working significantly harder than their peers to accomplish the same motor tasks. This reframes the daily frustrations that characterize dyspraxia. When your child takes 20 minutes to get dressed in the morning, they're not dawdling, They're solving complex planning problems with each button and zipper. When they avoid playground activities, they may be conserving cognitive energy for the academic demands ahead. The exhaustion that many individuals with dyspraxia report isn't physical fatigue, but mental fatigue from constant motor problem solving. For educators, this understanding suggests that accommodations should focus on reducing planning demands rather than simply allowing more time. Providing step-by-step visual guides for complex tasks, breaking multi-step instructions into smaller components, and offering alternatives to handwriting-intensive assignments can dramatically reduce the cognitive load of school activities. The goal isn't to lower expectations, but to remove barriers that prevent students from demonstrating their actual knowledge and abilities. The research on explicit instruction has practical implications for skill development. Rather than hoping that motor skills will improve through repetition alone, individuals with dyspraxia benefit from consciously learning the planning process. This might mean verbally rehearsing the steps of tying shoes, using visual schedules for morning routines, or explicitly discussing the spatial relationships involved in handwriting. Technology offers increasingly sophisticated support options. Voice-to-text software can bypass handwriting difficulties entirely. Tablet-based apps can provide immediate feedback for motor learning tasks. Some emerging technologies use haptic feedback or augmented reality to provide additional sensory cues during motor planning, though these remain largely experimental. For adults who recognize dyspraxia traits in themselves, understanding the condition can be profoundly validating. Many adults with undiagnosed dyspraxia have spent years believing they're simply clumsy or disorganized, developing elaborate compensation strategies without understanding why basic tasks feel so difficult. Recognizing dyspraxia can explain long-standing challenges and point toward more effective coping strategies. The workplace implications are significant but often overlooked. Adults with dyspraxia may excel in roles requiring creative thinking or verbal skills, while struggling with tasks involving fine motor precision or complex sequencing. Understanding these patterns can inform career choices and workplace accommodations. Simple modifications like ergonomic keyboards, voice recording for note-taking, or flexible deadlines for tasks requiring motor precision can level the playing field. Perhaps most importantly, understanding dyspraxia as a neurological difference rather than a deficit changes the conversation around identity and self-worth. Individuals with dyspraxia often develop remarkable problem-solving skills, persistence, and creativity, precisely because they've had to find alternative approaches to everyday challenges. These strengths deserve recognition alongside acknowledgement of the genuine difficulties the condition creates. Your brain orchestrates thousands of movements every day through an intricate planning system that most people never consciously experience. In dyspraxia, this system works differently. Not broken, but requiring more conscious effort and alternative strategies to achieve the same goals. The child who struggles to tie their shoes isn't clumsy. They're navigating a complex neurological landscape where the pathways between intention and action require constant, effortful problem solving. Understanding this distinction transforms how we support individuals with dyspraxia, moving from simple practice to strategic planning, from accommodation to empowerment. The motor planning challenges are real, but so is the remarkable adaptability of the human brain when we work with its differences rather than against them.